So as we're going to start our little overview of statistics, we're not going to go into huge depth about it, but we're going to talk about some of the real basics. So first off, what is statistics? That would be a great question if it's a question that you had. So statistics is the first blank. I wasn't super creative with that one. Statistics is the science of gathering, analyzing, and making inferences from numerical information obtained in an experiment. So statistics is done on numbers. Okay, so that is significant as you're looking at this. And there's all sorts of different facets of statistics. So gathering is some statisticians focus on gathering appropriate data. Is my sample size big enough? Am I measuring what I think I'm measuring? What is my level of certainty about this data? Analyzing, describing some characteristics, and you're probably familiar with a couple of the words as far as analyzing data. And we're going to take the briefest of views, and then making inferences, like what kind of predictions can I make and can I not make based on the data that I have? Is it telling me the things that I think and hope it is? So this numerical information that we gather through our experiment, that's called data. So the numbers that we work with are called data. And there are two big broad branches. You can get as specific as you want in the study of statistics, but there's two big broad branches of statistics. The first is called descriptive statistics. That's where we're going to focus our brief efforts in this chapter, is on descriptive statistics. And what it is concerned with is the collection, organization, and analysis of data. Now, as far as us, we are not going to actually collect any data. We're going to talk about good and bad ways to collect data. We'll talk a little bit about the organization and analysis of data. The other branch that we are not going to talk about in this class is inferential statistics. It's concerned with making generalizations or predictions from the data collected. So if you're interested in that, the statistics class we offer here does some basic inferential statistics about, can I make predictions? What are my confidence intervals? Things like that as far as my statistics is concerned. Now, what you're doing when you study statistics is you're studying what's called a population. And a population is everything available to be studied. Now, populations can be big or populations can be small. For instance, if I was studying the grade point averages of Polk State students, then my population would be Polk State students. Okay, so that's sort of a bigger population, but not huge. If I was studying the grades of university and college students throughout the United States, that's a bigger population. Okay, so populations can be as narrow or as broad as you would want them to be. Now, the bigger you make the population you're studying, the harder it is to study. And so that's where statistics comes in. When you have a population that is too large to do a survey of every single element of it, what you do is you take a subset. Okay, and a subset of the population is called a sample. So if you were in a class and you needed to do a survey and you needed to see what maybe Polk State students' thoughts were on a certain issue, you probably would not be able to go and ask every single Polk State student. So what you would do is you would design some sort of sample that represented the Polk State community well. So you would pick something that was manageable for you to use, and you'd have to take different things into consideration. You'd have to take into consideration we have 2 campuses and we have 3 other centers. You'd have to take into consideration that the populations of students that take day classes and night classes are different. You'd have to take into consideration different degree programs. So there's lots of things if you wanted to adequately represent in your sample the population, even of something as kind of small as Polk State. Okay, so there's some ways that you can take samples that are good basic ways to design a sample. So we're gonna talk about that a little bit. So we're just gonna go through some of these what's called sampling techniques, just to kind of get, again, we're just getting a little overview. So the first kind of way to sample a population is to do what's called a random sample. And what a random sample is each item is selected with an equal chance of being picked. Okay, so each item is selected with an equal chance of being picked. I wanted to give you something to write because we're already going to blow through this section pretty quick, but I wanted to make it worth your while driving out to the campus today. So I didn't want to let you go in like 5 minutes. Okay, so random sample. And so one of the important things about statistics is you don't want to accidentally favor something over another. And so in statistics, it's very important that you are giving every element of a population an equal shot, because again, thinking about our Polk State example, the sample you want to design in such a way that it adequately reflects the entire varied population of Polk State students. So one way to do that is to design a sample using a random sample. The next one's called a systematic sample. And what a systematic sample is, you select a random starting place, and then you select every nth item. So you decide, I'm going to pick every 10th or every 20th item. So you select a random starting place, and then you pick every nth item. That's why it's systematic. You're doing the same thing. That way, because you're doing the same thing, you're not favoring any one thing. So kind of a common example is if you worked somewhere where you are bottling things, like I live up in Lake County, and we have a water bottling plant for Niagara water. And I am certain that they have somebody on that line, because you got to make sure that the machine's filling up the bottles the appropriate amount. I'm sure they have somebody on the line that picks every nth item, every 100th or every 150th bottle of water, and just examines it and measures it and weighs it and makes sure that it is full to the appropriate amount, so that it's not false advertising, that you're actually getting whatever, a pint or a quart or whatever amount is in the bottle. So that would be a systematic sample. Now, these next two kind of sound the same, so want to make sure that you are clear on what the difference between the two is. The first one's called a cluster sample. Some books will call this an area sample, which is kind of the key word. I'm going to underline the word area. So as we go through these next two, the distinction between a cluster sample and the next one called a stratified sample is a cluster sample deals with area. And so what you would do for a cluster sample is you would first divide a population into geographic sections. Okay, so you would divide a population into geographic sections. Then what you would do is you would randomly select some number of those sections. So then you would randomly select some number of the sections. And then you will either choose all or a random sample from the sections that were chosen. move this over so you can see it. So first, somehow by area, you divide a population up by geography. So whether you're studying a state and maybe you use the county divisions, or maybe you have a map and you box it off into equal sized boxes, some way you're dividing a geographic area up into sections. Then what you're doing is you don't pick all of the little boxes that you have, you randomly select some of them. And then those ones that are randomly selected, you either pick all of the elements from it or you pick a sample of the elements from it in order to study a population. And we're going to have some examples on the next page so you can kind of get a feel for what this looks like. And if you still don't understand, then please feel free to ask me whatever questions that occur to you about what's going on here. Now, what that's opposed to, or what that's different than, but sometimes we get them confused, is what's called a stratified sample. And the reason that they're easy to confuse is because in a stratified sample, again, we divide up the population. But in a cluster sample, it's always area. In a stratified sample, the population is first divided into some characteristic. Okay, so the population and that characteristic that you're dividing the population up into, that's called the strata. Now, without knowing it, you're probably super familiar with this. Anytime you fill out a survey, like you go to a convenience store and they give you a survey, maybe you're trying to win that Chick-fil-A free chicken sandwich, so you fill out the survey. What they do at the beginning of that survey is they ask you some things so that when they divide their data up by strata, they can know, are there any trends in different populations? So, you know, the first question you usually ask is, what's your age? Or what's your race? Or what's your gender? Or whatever. Those are strata. That's dividing your population up by different characteristics. So just some examples, almost anything can be a strata. So some common examples are age and race and national origin, economic status. You know, you fill out your household's yearly income on some of them. It just depends on what different places are trying to measure. And just trying to see if there's any relationships, because that's what statistics tries to do. So first thing you do is the population is divided into some characteristic called the strata. Then a random sample from each strata is selected. So if you were designing an experiment to test some new drug or something, you would do this. You would want to know how this drug affects depending on age, depending on medical history, depending on any other sort of thing. And so that's why sometimes it costs a lot of money to develop a new drug, is you've got to do so much testing, and you have to do it in a variety of ways to make sure that you're actually interpreting the data and getting the relationships that actually exist. So those are, as far as this class is concerned, we're just trying to, again, get an overview. If you want to go deeper in stats, you will. If you're going to go into any sort of teaching program, if your goal is to be an elementary school or middle school, high school teacher, I am sure in your junior or senior year, you will take a statistics for teachers class, talk about test design, gathering data from students and things like that. So you'll get more specific to whatever curriculum you're going to have. So these are kind of the four good overview topics of ways to take samples. The next one, just by its name, you would probably judge is not going to be the best one. Convenience sample, what happens, but it's used a lot. This becomes a problem. So anytime a convenience sample is taken, you're automatically saying, okay, I'm not too serious about the statistics and what I'm doing here. A convenience sample just uses data easily attained. The priority is not good data. The priority is just having any sort of data. So for instance, if I was designing a study to study Polk State students, you all would be easy data for me to obtain, right? I just hand you out a survey, and since we're all sitting here, you'd have to fill it out. But the problem is then that gives some, if I'm being lazy, maybe intentional, but it brings in some unintentional biases into my statistics, okay? Because you, although you're wonderful people, are not representative of the full population of Polk State students. Okay, so just from what I know of Polk State, in this room, we have a higher percentage of women than our overall, the whole Polk State College. You're young, so that's different than the entire population of Polk State. So I would be unintentionally bringing in some skew into my data and my results. And so any projections I make would not necessarily be true of the whole Polk State experience. So some types of convenience samples, some types of bad ways to collect data. Here's like the most popular one, what's called a self-selected survey. A self-selected survey is like the one they email to you and they say, hey, if you fill this out, we're going to give you a gift card, or we're going to put you into a drawing for a gift card or something. What a self-selected survey is when you choose to participate. Okay, so that then again brings into a little bit of a slant into your data, because now you're getting people that are motivated to respond. And a lot of times when you do a survey, like if I went on a cruise over spring break, then I got a survey. People who respond to surveys most of the time are people who have a high emotional response, either really angry about something or really excited about something. So again, you have brought into some sort of consequence. So self-selected surveys, bad data right there. They don't tell you much. They don't really have predictive value, but they're an easy way to get a lot of data. That's why they're used. When you, I don't know, like if you ever have gotten one of the phone calls from some company, when it's about election time and they're starting to ask you questions about election and candidates, things like that. A lot of times what they are guilty of, and I have no dog in the fight here. Both sides of any argument do all of these same things wrong. Okay, so there are leading questions. And what a leading question is it's a question asked in such a way to get you to make the response that they are looking for, right? So again, no matter how you feel about this issue, I'm not trying to change your mind on anything, but if I asked you a question about how you feel about gun ownership, and I said something like, how do you feel about people owning guns when so many people are killed every day? Right? I am now injecting a bias into the question. I'm leading you to the conclusion that I want you to come to. And so again, my whole goal is I just want you to think about things, and I don't want you to be susceptible to people manipulating you. One of the things you should always do when you look at data, like when somebody presents you data for something, you should always look at what's the source of that data. Right? Like if the NRA gives you some data on gun ownership, okay, there's a reason for skepticism. Just like on the other side, if whatever organization that doesn't want anyone to own guns gives you some stats, you should be skeptical, okay, because they're going to have some biases in it. So just asking you to be cautious, and it's all about the misuses of statistics. Another thing that can happen in a convenience sample is using a small sample size. If you do take statistics beyond this, you will talk about something called a confidence interval. If you want your data and your conclusions to have the ability to be confident in what you're predicting, then you have to have a certain sample size based on how confident you want to be. And that's related to the size of the population and things like that. But what a lot of people are guilty of is you just, again, being convenient, you just take too small of a sample size. So again, your data is worthless when that. And then one other thing is, and I could go on and on because there's tons of ways to use statistics poorly. That's kind of the danger of it, is if you use vague or ambiguous words. If you're using a word in one way, but like people that you're asking are going to automatically think that you're using it another way. Okay, that's a misuse of statistics. A couple of the common ones are saying something like average. We're going to learn next week that the word average is really an umbrella word. It refers to several things that you could do. So me as a math person, I know that, but you as someone who might not have studied it as much, I know you're thinking one particular thing when you hear the word average. Right, you're hearing add them up, divide by how many things there are, because that's what we most commonly associate with the word average. So I could present you some data, and I could say the average is this, and now in your mind you've got one thing, but the average I could be referring to could be measuring something totally different. We're going to talk about 4 different types of averages when we come back next week, and each of them measures the center of data in a different way. And we'll talk about what that means. Another one is just using words that are more opinions than anything. So like the best or something like that, or worst. When you see those words, your red flag should go up that this is statistics being done poorly. If we had more time, statistics is a fun class and it's very useful. If we had more time, then I would kind of beat this point to death right here is this next thing because this is a common mistake people make when they are reading studies or when they're presenting or interpreting. The idea that correlation is not equal to causation. You always have to be careful when somebody is telling you definitively that 2 things are correlated. That means one thing causes the other thing. Okay, so correlation does not necessarily mean causation. They might be related by some other thing that you have not measured. So for instance, my example of this is a few years ago, I read on one of the news sites, and the headline was, "Diet sodas cause obesity." Okay, and what had happened is somebody did a study, and they found that there was a correlation. There was a relationship between the weight of people who drink diet soda. Okay, and I drink diet soda. Okay, so this interested me. Well, what it is the person saw that there was a correlation, and then automatically assumed that means that the diet soda is making people larger. But that's not necessarily true. What they didn't measure for or account for is I drink diet soda because I'm already a very large person and I don't want to be larger, right? So there is a different factor that goes into that relationship that hadn't been measured. So just a simple example of being careful whenever anybody says that these 2 things seem to be related, so one's causing the other. In all honesty, again, I'm not telling you what to think here. I'm just telling you to think about it. Bad statistics is prevalent beyond any shadow of a doubt in the climate change debate. On how is the climate changing? Does man affect it? Okay, I'm not going to tell you what the answer to that question is because I don't know, but I do know that when you look at the statistics, it's manipulated on both sides. People who say we need to be alarmed and freaking out, they're manipulating the data, and people who say there's nothing to worry about, let's sit back and chill, they are manipulating the data because everybody has an agenda. So again, that's all I'm trying to communicate to you is just be careful of people's agendas when you are dealing with statistics. All right. Well, I just vomited out a whole bunch of words to you. Sorry about that. I don't always just like to make this about me. So here's what we're going to do. I got a couple of examples here just to go through those 5 different sampling techniques and to see if you can identify them. So as we go through, if you have any sort of questions, because something isn't clear, then that's great, because we're actually almost done with this section. So we've got a preponderance of time today, so there's no rush. So I'm going to do the first 2 of example 1 with you, and then I'm going to set you free to do the other 3. And then so the example 1. Every 20th soup can off an assembly line is checked for defects. Which one of the sampling techniques would you think that is? Yeah, systematic. Okay, I'm checking, I'm doing a systematic check. I'm checking every 20th. That's how we know there. So an appropriate question as we're going through this, because I'm going to do the same thing on the test, although it'll be multiple choice, is I'm going to give you something and I'm going to ask you what sampling technique is this? So if you don't understand how we've identified it, please ask me. The B problem says a $50 gift certificate is given away at a bankers convention. Tickets are placed in a bin and the tickets are mixed and the winner is drawn by a blindfolded person. What kind of technique is that? Yeah, that's random. We're assuming that all the tickets in the bin have an equal chance of being selected, so that is a random sample. Great job. Okay, I'm going to give you about 90 seconds. Go do the C, D, and the E problem, see how you do, and then we'll talk about them. Okay, so the C problem says, children in a large city are classified based on the neighborhood school they attend. A random sample of 5 schools is selected. All the children from each selected school are included in the sample. Which one do you think that is? Why is that cluster? You're 100% right. Yeah, the neighborhood. I'm just going to underline the word neighborhood, the neighborhood school. It's geography. Okay, that is the key to identifying the cluster sample. Is it's based on some sort of area. So we're looking at the schools they attend. We're randomly picking some schools, and then we're taking data from all the children in each of the schools. Great job. D, the first 50 people entering a zoo are asked if they support, and that should be the word and, not and, I can't type, an increase in taxes to support zoo expansion. Yeah, that's convenience. So you can see how you can unintentionally, through the convenience sample, or maybe it's intentionally, I don't know, but I'm going to assume it's unintentionally, insert some sort of skew in the data, because you would think people that are lined up to go into the zoo, they're going to be more favorable to supporting zoo expansion, right? So then people who maybe don't go to the zoo. So unintentionally, you're not representing the population very well. Last one, all registered vehicles in the state of California are classified according to type, either subcompact or compact, etc. And a random sample of vehicles from each category is selected. That's what? Stratified. So the strata are the vehicle sizes, and then we take a random sample from each. Anybody got a question about any of those? All right, then example 2 gives you 5 more just to solidify this. So I'm going to give you a couple minutes. Go ahead and go through those 5, please. All right, so the first one, bingo balls are in a bin and they're shaken, and then one is selected from the bin. What do you think? Yep, random. Every bingo ball has an equal chance of being selected, so that's good. States divided into counties. You can keep reading, but I'm going to stop. What kind is that? Cluster, it's based on area. Didn't even need to read any further, but going on, a random sample of 12 counties is selected, and then a sample from each of the 12 counties, excuse me, a random sample from the people from each of the 12 counties is selected. That's cluster sample. Every 10th Samsung television coming off an assembly line is checked for quality. Yep, for sure. Viewers of Netflix are classified according to age, and a random sample of viewers from each age group are selected. Yep, great. And last but not least, the student government at a college is electing its president. The first 25 people leaving the library are asked whom they will vote for. Yeah, that's convenience. Great. All right, so just a couple of other things, and then we'll mop up this section. So again, my whole goal is I just want you to think about things as because there's so much bad math and bad stats out there. One of the most common ways to present bad statistics is with bad pictures, because we're visual people. You know, we think in pictures most of the time. So immediately when we see a picture, our brain is forming conclusions over it. So when you look at these two graphs represent the same information. What is the difference? What are you intended to think about one graph over the other? Well said. I'm just going to repeat it for the people who are watching on the video, but you did a better job than I will do, I promise you. And so what was said in class is the one on the left makes the change not look as drastic. The one on the right, the change looks much more significant. And the way it's been done is because on the y-axis, the scale has been messed with. Okay, so the scale is not complete. This is done all the time. It is one of the most common misuses of statistics because, again, it leads you to a conclusion that is not necessarily true. Okay, that there is some sort of huge drastic change going on. It doesn't have to just be the y-axis. In all honesty, one of my pet peeves is on the climate change temperature analysis. They leave out the x-axis. The year range is not long enough, because you can scope in on any segment of years, and you can either look like the Earth is on fire or the Earth is freezing if you just narrow in on any range. So you've got to be careful, and you got to make sure you are getting an appropriate scope. So changing the scales in order to make a graph look more or less dramatic is a huge misuse of statistics all the time. I'm going to flip the page. I got a couple more examples of this. Again, this next one is just done with bar graphs, the same sort of thing. But again, looking at it, the one on the left is the graph that's done wrong, and the scale is wrong. But what is the conclusion that you are supposed to come to between those two things? Right. In fact, what we're going to learn next time we're together on Monday is how to draw a proper bar graph. And the bars, the areas of the bars should be in proportion to the amount. And so our brain naturally does this, even if you don't know the numbers behind it. Look at this. So this one says, okay, if I divide the pink graph into about segments that are equal size to the other one, it makes it look like the pink one's 5 times more, right? That's significant. But you look over here, and that's not really true. Now, there is a little difference, and I don't know if that's significant or not because it's a made-up graph, and so I don't know what they're measuring. So it might still be significant, but the difference is definitely not as drastic as you're led to believe over here. So again, be careful when you're reading graphs that what is being presented to you, as you're trying to critically think. This one, I've actually seen this one done, and I had an example in my book, but it got all torn up. So again, this is just made up numbers, but the areas are supposed to communicate to us because it's a picture. But notice the number, it goes from $1 to $2. That's a doubling, right? So whoever made this graph, though, because it was doubled, instead of just doubling in one direction, they doubled in both. So how many times bigger is the green area than the orange area? It's actually 4 times bigger, not twice as big. What they should have done is either left or right or up and down. If you wanted to do the graph properly, you should have just doubled one dimension. So this would have been the proper thing to do. That would give you the proper relationship between those two things. The one that I saw, I need to see if I can still find it online and print it again. It was done by, I don't even remember the website, but it was comparing the space budgets of different countries, right? And so that it had boxes, these just like this. And I don't remember the countries, but it started off with a real tiny one. And then of course the United States had this ginormous box that took up half the page. And so the intent is to show how much more we spend on this than other places, which is a true statement. But the visual representation didn't match the numbers. And so whoever made the graph had extended both the length and the width and got a visual representation that was much more dramatic than it actually was in reality. So I just thought it was interesting because it was about space, and you would think space people know all about numbers. So it wasn't true in that instance. So the last thing here is an example of a pie graph. And a pie graph, again, when you see a pie graph, each sector of pie is supposed to be designed to represent the percent. So when you're visually, whether you're looking at the numbers or not, and you look at these pies, you can say, oh, this pink piece of pie is way bigger than the orange one. So it has a relationship. But here's the key, and this also happens a lot. If my circle represents everything that can happen, what should all the percents add up to in a pie graph? Yeah, it should add up to 100%. Now, this is a dramatic example that the book gives just to reinforce this point. I think the book's example adds up to 150%. I've never seen it be that wrong, but your pie graph shouldn't add up to 95%. It shouldn't add up to 107%. It should add up to 100%. So if you did scan the numbers and add them up and it added up to more or less, then something's wrong. It's bad statistics. So because this is so prevalent, okay, and just want to offer you this little bonus assignment because I know we're going into the last test and everybody wants as many points as possible. So here is your little bonus assignment. By the next test, you can just bring it to me on the day of the next test, not after. I won't accept it after the next test. You're going to submit examples from your reading, whether this is a book you're reading, a textbook, online, magazines, news sites, whatever, Twitter. Oh man, you can go to Twitter, you can do this assignment in 4 minutes. Okay, so misuses of statistics, whether it's one of the sampling techniques or whether it's a bad graph or something like that. You can submit to me links or screenshots or printouts or whatever. Just get with me so that, like, if you're going to send me screenshots, send them all in one email so I have them all together. And so I'll give you 2 points for each one you send me, up to 10. Okay, so you can get a maximum of 10 points, so a maximum of 5 of whatever you're going to send me. So just again, my whole point in that little bonus assignment is I just want you to, as college students, as people are going to be going out into the world, I just want you to begin to develop the ability to look at things critically, because I know sometimes we look at numbers and statistics and we think, oh, that's got to be right because there's percent signs, and it doesn't always have to be that way.